Now we're going to begin talking about acceleration mathematically. So we've talked a lot about what acceleration is. We know it measures how quickly the velocity of an object changes, but let's think about how we would actually put that into equation form. So in equation form, there's really two things that are going to matter. Number one, it's how quickly the velocity changes. So the amount the velocity changes is going to matter. And the other thing that's going to matter is this how quickly piece, which really is saying what is the time. So as we said on the previous slide, mathematically the acceleration is going to depend on the change in velocity, so how much we speed up or slow down. And it's also going to depend on how long it takes that change to occur, the time over which we are speeding up or slowing down. So the formula we're going to use here to calculate acceleration when we're dealing with the speeding up, slowing down part is this: A equals VF minus VI over T. We'll talk a little bit later about how we deal with the changing direction piece, because that is the third way to accelerate, but for now we're just going to focus on speeding up and slowing down. So in this formula, A is going to be our acceleration, VF and VI are going to be our initial and final velocities, and T is going to be the time over which that change occurs. Now that we've begun doing some math in this class, it's a good time to talk about units. Units matter, okay? Every single number that we deal with in here, with the exception of a few unitless quantities that we're going to talk about later in the year, should have a unit on it. Okay, the unit is like clothing for the number. If we have a number without a unit, it's naked and it's offensive, and on top of that, the unit gets cold. Okay, you have to put units after every single number. Now you probably remember from chemistry class that there is a standard set of base units in physics and really in science in general called the SI units. So the standard unit for distance, the standard SI unit, is the meter, and the standard unit for time is the second. All right, that means that velocity, which is a distance over a time, okay, is in meters per second in physics class and in science in general. We don't use miles per hour, we use meters per second. All right. So based off of that previous equation and what you now know about the standard for distance and time, think for a second about what the units for acceleration should be. So if we think for a second about our equation, which we have here, VF minus VI over T, and just think about the units that we're going to have, what that ultimately is going to result in is on the top of that fraction, we're going to have meters per second, right? That change in velocity is going to be measured in meters per second, and that time is going to be measured in seconds. So one way you'll actually see the units for acceleration written is this: meters per second per second. And although that's an improper fraction and your math teacher might not like it, that actually really gets at the heart of what acceleration is. Okay? If we have an acceleration of 5 meters per second, that means that every second our velocity is increasing by 5 meters per second. All right? However, what we usually do is we simplify this fraction. We multiply the top and bottom by seconds, and that ends up getting us a unit of meters per second squared. And so that's typically how we write it, although if you write it as meters per second, I'm certainly not going to take off points. And I actually, in some ways, like I said, like that because it really gets at the heart of what acceleration is, how much our velocity is changing in a given period of time. All right, so we have 3 practice problems here. What I would suggest is that you go ahead and try those 3 and then check them. I'll go through them one at a time, but pause the video for a second, try those 3 problems, and then play it again, and I'll go over the answers. So starting with this first one, we have a car slows down at a rate of 2.8 meters per second squared. How long will it take the car to come to a stop if it is initially traveling at 15 meters per second? So I'm going to start by identifying what things I know. This is the equation I'm going to be using, A, because it's the only one we've learned so far, but also that links acceleration to velocity. And so things I know it's initially traveling at 15 meters per second. Okay. I also know that it comes to a stop, and so even though it doesn't explicitly say that, that's telling me that my final velocity is 0. All right. The last thing that I know is that my acceleration is 2.8 meters per second squared. However, if you just write that, you're not really thinking about your concepts. You're not really reading into this problem. This tells us a very important thing. It tells us that the car slows down at a rate of 2.8 meters per second squared, which means I need to indicate that my acceleration and my velocity are in opposite directions, because that's what happens when you slow down. So that acceleration actually needs to be a negative 2.8. And that's going to make things work out correctly mathematically. Otherwise, I'd end up with a negative time, which we can't have. Now that I know those things, I'm going to plug in what I know. So I have negative 2.8 is going to be equal to 0 minus 15 over t. I'm going to go ahead and cross multiply here, and so I get negative 2.8t equals negative 15. And so I find here that my time just ends up being 5.36 seconds. Notice I have that unit there. We got to make sure we put that unit at the end of the problem. Moving on to my next one, I'm going to start once again by identifying the things that I know. So I start here with a velocity of 25 miles an hour. I speed up to a speed of 35 miles per hour at a steady rate over a period of 8 seconds. The first thing I should notice here is this 25 mile an hour bit. Okay, I know that I want my units to be in meters per second. That is my standard, and I see here too that the problem even specifies that the acceleration should ultimately be in meters per second squared. So the first thing I'm going to have to do is convert those two velocities to meters per second from miles per hour. So I go ahead and set up that conversion, right? 1609 meters in 1 mile and 3600 seconds in 1 hour, and I see that that'll cancel out the miles and that'll also cancel out the hours. Certainly you could go to minutes first and then seconds, but what I end up getting here is that initial velocity is actually going to be 11.17 meters per second. And that final velocity is going to be 15.64 meters per second. I can now go ahead and use my equation, Vf minus Vi over t, to solve for my acceleration. So I can say that my acceleration is going to end up being 15.64 minus 11.17 all over 8. And so I get an acceleration here of 0.56 meters per second squared. One quick note, and maybe you picked up on this, when I'm actually doing the problem itself, I don't put the units next to the numbers. That's just mainly because it gets a little bit cumbersome and there's a lot going on, but in the final answer, you absolutely should have your units. All right, for the last question here, once again, I'll identify my variables. And this one is one where you really have to read into the problem pretty carefully here. So the first thing that I know is that my initial velocity is 1.5, but I'm going backwards, and so I need to indicate that, and so I'm going to do that by saying that my initial velocity was negative 1.5 to indicate the direction. We then accelerate to travel forward at 4 meters per second. Since it's 4, that's going to be a positive 4, and that occurs over a period of 3 seconds. Okay. And so I can go ahead and set up my equation now. Acceleration is Vf minus Vi over t. All right. And so it's going to end up being acceleration is 4 minus negative 1.5, which really means we add over 3 seconds. And so I end up getting an acceleration here of 1.83 meters per second squared. One last thing here, and this is something that a lot of you probably already know, but just a quick calculator tip. A lot of times when we do these, it's easier to pull a number from a previous answer rather than typing it in exactly. So there's 2 ways you can do this on one of the TI calculators. You can either do second and then the minus sign, and what that does is it will display the word ANS for answer, and that will give you your previous answer, whatever the answer was to the previous thing you typed in. Or if you have the newer software on the TI-84, you can use the up and down arrows and select the value. Like I said, I know a lot of you probably know that, but I just feel that I should point that out at this time.